Look closely at any physical object, and it seems entirely solid. A grain of sand or graphite behaves like a discrete, predictable thing. But as we zoom in, that certainty begins to break down, revealing a landscape that behaves less like objects and more like ripples. In 1801, Thomas Young fired a beam of light through two narrow slits. On the wall behind it, the light didn't form two bright spots. Instead, it created an alternating pattern of bright and dark bands, the signature of overlapping waves. For over a century, this was the accepted proof that light was a wave. But in the 20th century, physicists ran the same experiment using solid matter, firing individual electrons through the slits. You'd expect them to land in two clusters. Instead, random impacts accumulate over time, building that exact same wave interference pattern. Even though they arrived as single particles, they traveled as waves. At this scale, the building blocks of matter exist as waves of probability until the moment they are detected. Naturally, physicists wanted to see this transition happen. They placed a detector at the barrier to catch exactly which path the electron takes. The moment the detector is turned on to extract that path information, the wave pattern vanishes. The electrons stop interfering with themselves and form two solid, distinct bands of particle impacts on the back wall. The act of extracting information forces the system to abandon its fluid wave state and lock into a definite physical reality. If the particles that make up our bodies act like waves, it raises a question. Why don't everyday objects, like baseballs or people, ripple and interfere with each other? To find the boundary where this behavior stops, researchers at the University of Vienna tested carbon-60 molecules, known as buckyballs. With 60 carbon atoms and 174 internal vibrational modes, this is a massive, complex object, far closer to a classical body than a single electron. The team had to isolate the molecules from the outside world, firing them through a grating inside a heavily shielded high-vacuum environment. When perfectly isolated in that vacuum chamber, even these massive molecules behaved like waves, successfully interfering with themselves. Physical size alone does not destroy quantum behavior. Something in our everyday environment is actively collapsing the wave. This process is called decoherence. It is the concept that the environment itself acts as a detector, collapsing quantum waves without the need for a human observer. This chart shows the process. Graph A measures interference visibility against background gas pressure. Gas molecules bump the buckyball, leaking path information and destroying the wave. Graph B shows heat does the same. Emitting infrared photons gives away its position, collapsing wave visibility. The classical reality we experience emerges because macroscopic objects are constantly interacting with their surroundings, leaking information that instantly collapses their quantum waves. If the universe is governed by the exchange of information, there is one more boundary to test. What happens if we extract the path data after the particle has already finished its journey? This is the delayed choice quantum eraser. It uses a specialized optical setup to create pairs of entangled photons. One signal photon flies to a screen, while its entangled idler twin is used to track its path. If the idler's path is measured, the signal photon acts like a classical particle, hitting the screen in a random scatter pattern with no wave interference. But if that idler's path information is destroyed, the wave pattern is restored. Erasing the data doesn't rewrite the past. The original scatter plot never changes. Instead, sorting the signal impacts with the erased idler data reveals a hidden interference pattern. The outcome of the experiment depends on the availability of information. By sorting the data after the fact, researchers can recover a quantum wave pattern from a result that initially appeared entirely classical. Research into the double slit has traditionally focused on physical gaps in space, but at Imperial College London, scientists have moved the experiment into a new dimension by attempting to slice through time. They fired light at a material that changes its reflectivity in fractions of a femtosecond, creating temporal gates, time slits, opening and closing with ultra-high-speed intensity. Because these slits were separated by time rather than space, the interference pattern didn't change the light's direction. It shifted the light's frequency, causing it to change color. The double slit experiment suggests that space, mass, and time are fluid constructs. They only lock into a solid, classical reality the moment the universe is forced to share its secrets.